The Andromeda Galaxy played a pivotal role in reshaping our understanding of the universe and our place within it. Our galaxy, for example, is the Milky Way galaxy, and the nearest galaxy to us is the Andromeda Galaxy. We think there are about 100 billion galaxies in the visible universe. It served as compelling evidence that the cosmos and the concept of creation don't revolve around Earth. This discovery shattered the notion that the Milky Way was the sole galaxy in existence, suggesting that we are just a tiny part of the vast universe. While we have accumulated knowledge about Andromeda over the last century, much of it was gathered from observations made on Earth. However, with advanced tools like the James Webb Space Telescope now at our disposal, our perspective has drastically changed. Surprisingly, the recent data obtained from the James Webb Telescope has upended our previous notions about the Andromeda Galaxy, presenting another cosmic puzzle that needs to be solved. The JWST has received signals from our neighboring galaxy, leaving the entire scientific community astonished. Join us as we explore how the JWST received an alarming signal from our neighbor, the Andromeda Galaxy. Indeed, the perception of the Milky Way has undergone significant changes over the course of human history, shaped by our evolving understanding of the cosmos. In the past, when our technological capabilities were limited, the Milky Way appeared as a hazy band of light across the night sky, inspiring various interpretations and mythologies. It was often seen as a mystical and central element in the cosmological beliefs of different cultures. As our scientific knowledge advanced, particularly with the development of telescopes and the work of astronomers like Galileo Galilei, we began to realize that the Milky Way was not just a celestial concept but a vast collection of stars, planets, and other celestial objects. This realization revolutionized our understanding of our place in the universe. Today, thanks to modern telescopes and astronomical research, we have a much clearer picture of the Milky Way as a barred spiral galaxy containing billions of stars, including our own Sunday. In the 1920s, Edwin Hubble, an American astronomer, made a transformative discovery using the 100-inch Hooker telescope at Mount Wilson Observatory. Hubble observed distant nebulae beyond the Milky Way. Through the observations and analysis of these objects, he showed that they weren't actually part of the Milky Way but were entirely separate galaxies, each containing billions of stars. One of the closest of these galaxies was the Andromeda Galaxy, also known as M31. The Andromeda Galaxy has a rich history of observations that dates back centuries. One of the earliest known records of this celestial object can be traced back to the 10th century, when the Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud in star charts from that period. The significance of these observations lies in the fact that al-Sufi was able to identify this distant cosmic entity without the help of telescopic instruments, relying solely on his keen eyesight and observations. It wasn't until 1612 that a detailed description of the Andromeda Galaxy, based on telescopic observations, was provided by Simon Marius. His work laid the foundation for future astronomers to study this massive cosmic structure. Later, in 1764, the renowned French astronomer Charles Messier catalogued the Andromeda Galaxy as M31 in his well-known Messier catalogue, mistakenly attributing its discovery to Simon Marius. However, that doesn't diminish Messier's role in putting Andromeda on the map. For almost 100 years after these observations, astronomers worldwide sought to understand more about this mysterious galaxy, each adding to the last one's findings. Before that, Galileo Galilei, an Italian astronomer, revolutionized our understanding of the Milky Way in the early 17th century. Using his newly developed telescope, he made groundbreaking observations that challenged the prevailing Italian cosmology. In 1750, English astronomer Thomas Wright proposed a new hypothesis in his work, an original theory or new hypothesis of the universe. According to Wright's speculation, the Milky Way was not a random distribution of stars in space, but a completely flat layer of stars. He also suggested that a portion of this vast structure was our own solar system. While Wright's hypothesis was a step forward in understanding the structure of the Milky Way, it was still limited by the observational technology available at that time. A significant leap in understanding the nature of the Andromeda Galaxy occurred in 1864, when the English astronomer William Huggins made a groundbreaking observation. He studied the spectrum of Andromeda and noticed that it was different from that of a typical gaseous nebula. This observation paved the way for the world to understand Andromeda for what it really is. The Andromeda galaxy has a mass estimated to be between 1 and 2 trillion times that of our Sun, making it a colossal cosmic structure that just happens to live relatively close to us in the vastness of space. In all the research conducted, the exploration of galaxies like Andromeda continues to expand our understanding of the universe and our place within it. Until now, scientists believe that Andromeda is about 10 billion years old, making it quite ancient in cosmic terms. One intriguing aspect of Andromeda's origin is the hypothesis that it came into being through the merging of several smaller protogalaxies. This suggests that, over billions of years, smaller galactic entities gradually came together under the force of gravity to form the majestic Andromeda galaxy we see today. Galactic mergers are common occurrences in the cosmos, shaping the growth and structure of galaxies. However, for a long time, astronomers thought Andromeda was significantly more massive than our own Milky Way galaxy. This misconception is understandable, considering the limitations of the observational tools available in the 1700s and 1800s. Recent research has brought about a reevaluation of these beliefs. New findings have led scientists to somewhat reduce their estimate of Andromeda's mass while simultaneously increasing the mass attributed to our Milky Way. The current understanding is that the masses of these two cosmic giants are much closer than previously thought. So if you were to be on Andromeda and looked at Earth, you'd see just as massive of a galaxy. This puts into perspective how colossal the Milky Way itself is too. The Andromeda galaxy's physical dimensions, though, are what astronomers totally agree on. It's known to stretch farther than our own Milky Way, with an impressive diameter of about 220,000 light-years. Andromeda surpasses the Milky Way's estimated diameter of roughly 100,000 to 175,000 light-years, making it a truly significant cosmic entity, taking over a large region in space. This revised perspective also highlights the complexities and challenges of accurately measuring the mass of galaxies. In the heart of the Andromeda galaxy, the supermassive black hole exerts an immensely powerful gravitational pull on surrounding stars. As these stars orbit around the black hole, they follow elliptical paths similar to planets orbiting the Sun in our solar system. At a certain point in their elliptical orbits, stars come close to the black hole, and this point is called the perihelion. At the perihelion, the gravitational forces are at their strongest, causing the stars to move at their highest speeds. This is when the stars bunch up and become more concentrated in space around the black hole. As they bunch up, the stars release energy in the form of radiation, including visible light and other types of electromagnetic radiation. The increased concentration of stars and the release of radiation create the brighter point of concentration that astronomers observe in the galactic core of Andromeda's active galactic nucleus, AGN. More on this later. This distinctive feature provides valuable clues about the gravitational dynamics and interactions between the supermassive black hole and the surrounding stars. To understand this better, let's take a look at what an AGN is. The active galactic nucleus, AGN, is a highly energetic region at the center of a galaxy. It is characterized by intense emissions across various wavelengths, from radio waves to X-rays. AGNs are powered by the presence of a supermassive black hole at the heart of the galaxy. These supermassive black holes are incredibly dense regions in space where an enormous amount of mass is concentrated within a very small volume. When astronomers observe the active galactic nucleus using advanced telescopes like the Hubble Space Telescope, they notice a very interesting phenomenon. One of the most fascinating features of the Andromeda galaxy is its AGN. It appears to have 2 points of concentration, meaning there are 2 distinct regions where light and other forms of radiation are emanating more intensely than in the surrounding areas. The brighter concentration is the second point of focus, which is just slightly off the true galactic center. Within this area lies the supermassive black hole. The mass of this black hole has been estimated to be between 1.1 to 2.3 times 10 to the power of 8 solar masses, which means it weighs approximately 110 to 230 million times as much as our Sun's supermassive black holes are believed to be common in the centers of galaxies, including our own Milky Way, and they play a crucial role in the evolution and dynamics of galaxies. When matter such as gas and stars gets too close to a supermassive black hole, it forms an accretion disk around it. This disk of swirling material heats up and emits intense radiation across various wavelengths, which is why the AGN is highly luminous. When astronomers observe the active galactic nucleus of the Andromeda galaxy, they notice a brighter point of concentration near the central supermassive black hole. This feature is a result of the unique gravitational interactions between the black hole and the stars in its vicinity. The Andromeda galaxy also has another super interesting feature: an abundance of globular clusters. These globular clusters are tight groups of stars that orbit around the center of the galaxy, kind of like satellites revolving around a planet. Andromeda is estimated to harbor around 460 of these dense and ancient clusters, each containing hundreds of thousands to millions of stars that formed around the same time. The incredible number of globular clusters in Andromeda offers valuable insights into its cosmic history and interactions with the surrounding environment. Smaller galaxies, over the course of billions of years, suggest that Andromeda has been an active devourer of these smaller galactic companions, a process known as galactic cannibalism. As smaller galaxies come within Andromeda's gravitational reach, immense forces strip them of their stars and other components. The stars from these cannibalized galaxies become part of Andromeda's stellar population, adding to the rich diversity of stars present in the galaxy. This characteristic of accumulating globular clusters and stars from smaller galaxies is considered typical for spiral galaxies like Andromeda. Spiral galaxies, characterized by their disk shape with distinctive spiral arms, provide an ideal environment for interactions and mergers with smaller companions. In addition to its other intriguing characteristics, recent observations and analyses have sparked speculation among astronomers that the Andromeda galaxy might be undergoing a fascinating transformation. It appears to be transitioning from being a typical spiral galaxy to a relatively rare type known as a ring galaxy. Ring galaxies are intriguing and relatively rare celestial objects characterized by their circular or elliptical ring-like structures. The rings consist of bright young blue stars, while the central region contains relatively little luminous matter. These unique features make ring galaxies stand out among the vast array of galactic structures. There are three main types of observed optical ring phenomena: nuclear rings, inner rings, and outer rings. Nuclear rings are located near the center of a galaxy, while inner and outer rings are a bit further out. There are two primary types of ring galaxies: O-type and P-type. O-type ring galaxies have centrally located nuclei, and their rings are smooth and regular in shape. P-type ring galaxies have off-center nuclei, and their rings tend to be more irregular. Ring galaxies are considered rare cosmic gems, with only approximately 1 in 10,000 galaxies classified as them. Astronomers have proposed two main mechanisms for the formation of ring galaxies. First, they can form through the collision of two or more galaxies. Second, a smaller galaxy passing through the center of a larger galaxy can also trigger the formation of a ring-like structure. Examples of ring galaxies thought to be formed through galactic collisions include the Cartwheel Galaxy, Galaxy Pair A 2026-424, and NGC 474. The most captivating revelation is the ongoing collision course between the Milky Way galaxy and the Andromeda galaxy. They are expected to merge, forming a new supergalaxy. This colossal event, already dubbed Milkomeda or Milkdromeda, has playful nicknames, but the consequences for humanity would be devastating. The merging process can trigger bursts of star formation in regions where gas clouds collide and compress, creating new stellar nurseries. These nurseries become the birthplaces of young massive stars fit for the new galaxy. As the galaxies merge, the night sky becomes a cosmic light show with stunning displays of star clusters, shock waves, and bright bursts of radiation. The collision and subsequent merging will create new constellations and stellar arrangements, transforming the entire sky. However, the effects run deep, impacting Earth's climate and weather patterns. Changes in temperature, precipitation, and weather events might occur worldwide, influencing the distribution of vegetation and animal habitats. The gravitational forces between the merging galaxies will distort each other's shapes, causing tidal interactions where stars, gas, and dust are pulled between the galaxies. Overlapping galaxies will lead to mayhem and destruction. The merging process initiates dynamic and chaotic changes within the newly merged galaxy, including the potential flinging of stars out of the new galaxy. Both galaxies harbor supermassive black holes at their centers, which will eventually merge as well, forming an even larger black hole at the heart of the newly combined galaxy. This merging could lead to disturbances in the solar system, impacting Earth's climate and weather patterns. Changes in temperature, precipitation, and weather events might start happening worldwide, influencing the distribution of vegetation and animal habitats. The shift in climate and habitats could interfere with migration routes and timings, leading to challenges in finding food, water, and suitable breeding sites. The altered atmospheric composition might influence photosynthesis and other essential processes that sustain life on our planet. Some species may thrive in the new conditions, while others may struggle to survive, leading to local extinctions and changes in biodiversity. While the merging process is a grand-scale event, the reality is that it won't happen overnight. The collision is expected to begin approximately 4 billion years from now, with the entire merging process taking another 2 billion years to complete. Long before this, around 5 billion years from now, our sun is projected to evolve into a red giant, rendering our solar system uninhabitable. The merging of galaxies and the subsequent changes in the cosmic environment will shape a new galactic structure, marking a profound transformation in the universe different from what we've always known. Within this merged galaxy, there may be star systems with planets orbiting in the habitable zone where conditions could be suitable for liquid water to exist. Liquid water is considered a crucial factor for the development and sustenance of life as we know it. However, the stability of the new galactic structure will play a vital role in determining whether life can thrive. The interaction between stars and potential gravitational disturbances might affect planetary orbits and environmental conditions, influencing the evolution and sustainability of life on any potential habitable planets. While the merger of galaxies can lead to increased cosmic radiation and stellar activity, including rare events such as supernovae and gamma-ray bursts, the actual occurrence of these events and their impact on planetary environments are difficult to predict. If life were to emerge in the new galaxy, it would likely undergo adaptation to the specific conditions of its environment. Different physical and chemical properties of the new galactic region could give rise to a unique form of life distinct from what we know on Earth. However, humans of today won't be able to survive in this new galaxy.